Very good morning to all of you. I hope by all the classes being held, you have learned something new. Every day we all are trying to educate you with some important concepts of physics, which when your regular courses will start, it will definitely be of great help in understanding the chapter in detail, right? So presently the concepts that have been dealt with, in that you have studied the basics of mathematics like trigonometry, calculus involving integration, differentiation, basic things about that. Then you saw about motion, you saw about something of current, electricity, you saw about optics, you saw about vectors, relative motion, right? Yesterday's class also for conservation of momentum. So in today's class, good morning again, today's class we will be seeing about another important point, which is known as conservation of mechanical energy. So we have conservation of mechanical energy. We have conservation of mechanical energy. Now when you see the word conservation, so you should know that what do we mean by conservation actually. So conservation word here simply means that the total energy is not going to go anywhere. It will remain with the body or the system of bodies, right? So when we first of all write the mechanical energy of any body or a system of bodies, mechanical energy we say is the sum of kinetic energy plus potential energy. This is the formula for mechanical energy. Now you all know that the kinetic energy, it has a value half mv square. Now this kinetic energy at any instant has half mv square value. This value either can be positive or 0. Kinetic energy can either be positive or 0, it cannot have a negative value, okay. Now talking about U, which I am writing for potential energy. Why I am writing? Because you will later on see that in most of the standard books, reference books, they say the potential energy as U, okay. Now as I said again, you don't have absolute formulas for some things. For kinetic energy also you are seeing half mv square, but later on when you will study in detail, you will see in a chapter rotation the formula also changes, some other formulas will come. Similarly, potential energy does not mean mgh, okay, always. Potential energy is not always mgh, it can be other things also, right? So we have to see what exactly it is. For example, if I ask you washing powder, that does not mean that it is Nirma. It can be Ariel also, it can be Surf Excel also, it can be Tide also. So potential energy is not just mgh. Try to understand what it is. So this is potential energy. Now when we say potential energy, this potential energy can be positive also, it can be negative also, or it can be 0 also, because this energy is dependent on the position of any body or any particle or any system. It is an energy dependent on position. So as per the selected reference point, so whenever we measure position, try to understand it. Whenever we measure position, this potential energy is due to, or you have studied in class 8, 9, 10th I think, that potential energy is due to position. So whenever we find the position, for that we select a reference. Reference means such point where we take its value as 0, okay. For example, suppose I tell you that there is a scale and this is the 0 centimeter mark, this is 1 centimeter mark, this is 2 centimeter mark, this is 3 centimeter mark, and one particle is placed here. This is the particle. Now if I ask you what is the position of the particle, you cannot say. Those who are saying, you cannot say. because I did not mention with respect to what. All of you are saying 2, you cannot say, because I did not mention with respect to what. If I say what is the position with respect to origin, then you will say 2. If I say with respect to 1, if I take 1 as the reference, then is its position 2? Is its position 2? Answer is no. Its position will become how much? 1 unit right of the reference. If I select 1 as the reference, then you will say its position is 1 unit right of the reference. If I take reference at 2 itself, will its position be 2? Answer is no. It will be at origin, because I will say that reference means where its value becomes 0. So if I take 2 as the reference, so you will say that its position with respect to the reference point is 0, right? If I go to 3 and take 3 as the reference, so I will say its position is what? 1 unit left of reference. Is it so or not? Tell me. So its position will be at 1 unit left of the reference if I take 3 as reference. So yes, that's what I am saying. When we select a reference point means where we take potential energy to be 0. So according to the selected reference point, your potential energy can be positive, negative and 0. Kinetic energy can never be negative. Kinetic energy is always dependent on the motion. It does not depend on the reference point or position. It is independent of reference position, and potential energy is dependent on reference position. Did you understand the basic difference between kinetic and potential energy? I hope this point is important and clear to all of you. Okay. Now, when we say this is the mechanical energy, then what happens? There are two types of forces. Forces we call as conservative and non-conservative. Conservative and non-conservative forces, what is the difference between these two? The difference is this type of forces, their presence cause loss of mechanical energy. Non-conservative forces are those forces whose presence cause a loss in mechanical energy, whereas conservative forces are those forces their presence do not affect the mechanical energy of a system. Mechanical energy remains unaffected. Mechanical energy remains unaffected by the presence of conservative forces, whereas if you have non-conservative forces, their presence cause loss of energy, and this loss of mechanical energy, where does it go? It gets dissipated in form of heat. The lost energy dissipates generally as heat, and that heat may further be converted into light or sound or other forms, but we say that the lost energy dissipates as heat. So whenever we talk of non-conservative forces, example, the best example we can talk of is kinetic friction, air resistance, air drag, etc. These forces are non-conservative forces. Whenever such forces are present in a system, they will cause a loss in energy. Whereas there are some forces which do not affect the overall mechanical energy of the system, means the mechanical energy remains conserved. Such examples presently we will be dealing with gravitational force, weight is also a gravitational force exerted by a planet. Weight, there is a force called spring force. These forces are what we call as conservative forces. So we have two types of forces. one are conservative, one are non-conservative, and in presence of conservative forces there won't be any change in mechanical energy. Yes, electrostatic energy, there is magnetic energy, correct? So there are other forces also. Presently we are taking these two examples because presently we are talking of mechanical energy, so we won't be going into the details of electrostatic or magnetic forces. Understood? Is this clear to everyone? Okay, so now as I told that potential energy, it can be plus, minus or 0 as per the selected reference point. So now we will quickly see two important examples or types of potential energy and the force involved, which is the spring force, which is the gravitational force. We will see that as well. Okay. Now next, when we talk important examples of potential energy, I have denoted potential energy as U, as I told. First we have gravitational potential energy, we will be denoting it as UG. So what we do, if acceleration due to gravity is assumed constant, we will later study in a chapter gravitation that if you go very high or below the surface of earth, G changes, but generally near the surface of earth G is assumed constant. So if G is assumed constant, then what we take ground level as a reference. Ground level we take as reference, ground level is H equals to 0. That means here we take the gravitational potential energy to be 0. So when you go at a height H, here the gravitational potential energy at a height H, we write it as mgh. So if you take a particle of mass m at a height above the ground, if you are taking the ground as reference, ground is taken reference, reference means your potential energy value at the ground will be 0. So when you go to a height h, your potential energy will become how much? mgh. Is it clear? This is one of the potential energies which we call as the gravitational potential energy. Similarly, we have one more important potential energy which is called elastic potential energy, which is stored in a compressed or stretched spring. So we have another object which is a spring. In that also we have a energy stored, we have an energy stored which is known as elastic potential energy, which is stored in a compressed or stretched spring. Now understand here, basically when we talk of a spring, we denote a position x equals to 0, we take it as a reference. Reference means this denotes no elongation or compression. It denotes no elongation or compression. So there is a spring and this length we call as natural length of the spring. When the spring does not have any elongation or compression, we take it as natural length and we denote this as x equals to 0. So here the potential energy, elastic potential energy, we generally denote it as us. So we will say in this case what happens, there is no energy also, there is no spring force also, spring force is also 0, there is no force by the spring, there is no energy stored in the spring. This is a very important point, remember. If the spring is at natural length, no elongation compression, there is no force, there is no energy stored. Is it clear? Now what happens if the same spring, this was the natural length, you pull it by x, you pull it by x. So in this case we will say this x denotes elongation, this x will denote elongation, and spring force has a special property by Newton's third law. Whatever you will do to the spring will do opposite to you. So what have you done to the spring? You have pulled it. Where have you pulled it? Forward. So the spring will do what? It will pull you where? Backwards. So there will be, if you pull this end by x, so spring force in this case will act oppositely. So there will be spring force Fs acting backwards. And it has been seen that this force is directly proportional to the amount of elongation. So we write this force Fs as k into x. We write this force as k into x. Every spring has a constant defined with it, which is known as spring constant. A spring has a constant defined for it, which is called as spring constant. So the force which will come in the spring will be kx. And what is its property? If you pull the spring will pull you back. So this is kx. And since this spring is elongated, it will have some energy stored in it. If it is elongated, it will have an energy stored in it, which later on you will see the derivation also when you will read this chapter. Presently we will just go by the formula of that. The energy stored in this case comes as half kx square. If the spring gets elongated by x, the energy becomes half kx square. K is a constant which is given a name which is called spring constant. So based on that, the energy in the spring is half kx square and the force is kx. What is the direction of force? Very simple. You pull a spring, spring will pull you back. Newton's third law. You compress a spring or push a spring, spring will push you back. I will show you that also, but presently. If from the natural length position you elongate it by x, the spring will pull you back by a force kx. And the energy stored in the spring is half kx square. Clear? Now, if, understand this thing, if this particular energy you want to actually know that it exists or not, so what we can do is you simply take a block, attach it over here in this position and leave the spring. What will you see? If I attach a block over here at this position and I leave it, what will you see? You will see that this block will start moving towards the left. If you pull the spring and leave it, you will see that the block will get pulled towards the left. So from where did the block get its motion? It got its motion from the energy which was stored in the spring. So that energy is half kx square. And whenever we are taking the spring energy, what is its reference? X equals to 0 is the reference. Because if you will put x equals to 0 here, you will see energy will become 0. So for spring energy, x equals to 0, natural length position is taken as the reference. Now we have a third possibility, that what if the spring was compressed, just like I said. This was the natural length position, x equals to 0. Now you have pushed it. So you have pushed or compressed by x. So if you push the spring or compress it by x, the spring will push you back. So where will be the spring force? Spring force will be directed outwards. So spring force again will become kx, but its direction changed. You push it, it will push you. You pull it, it will pull you. That's it. Very simple technique about spring. And in this case also, the energy stored in the spring has the same formula, whether you elongate by x or compress by x, the energy stored is half kx square. The energy stored is half kx square. Those who did not get, I think someone wrote what is x. So if you look at the diagram, if you would be seeing over here, I have told what is x. You can see very clearly it is written, x is elongation. If you see, x is compression over here. It is the amount of elongation or compression. I hope it is clear. So in any case, the energy stored in the spring is equals to half kx square. Clear? And the force is kx. It is directed always in such a way that you pull the spring, spring pulls you, push the spring, spring push you. Okay, fine. So now we will come to questions on this, but before that, still the point remains, what is the conservation of mechanical energy saying? So I said that if non-conservative forces are absent and only conservative forces are present, so what happens? If only conservative forces are present, non-conservative forces are absent, mechanical energy of a particle or a system of objects, whatever you select, this remains unchanged. So if this remains unchanged, that is, we can say mechanical energy at any instant is constant. So if mechanical energy at any instant is constant, this means kinetic energy plus potential energy will remain constant. This kinetic energy plus potential energy sum will remain constant. So this is what we call as conservation of mechanical energy, COME, conservation of mechanical energy. Is it clear? So you have to see which all forces are there. If the forces you see are conservative, you will say Ke plus potential energy remains constant. Clear? So let's see questions on this so that you get an idea of it. We start with a very basic question. There is a ball of mass m. It is thrown up with a speed of v naught. Now question is, find maximum height attained, find the maximum height attained, and second, speed at half the maximum height. Speed at half the maximum height. Now this is our question where we have to find the maximum height and speed at half the maximum height. Now this question can be directly solved by motion under gravity, but that too is a consequence of conservation of energy, because the only force which is acting in this case is gravitational force, and I told gravitational force is conservative. So what we can do is, if I take three positions on this, first here A, from where you threw the ball upwards, which was ground, here h is equals to 0, speed was v naught. Let's take point B, maximum height, h is maximum height. Now when you reach at the maximum height, obviously what will happen, your speed will become 0, your speed will become 0, and there is one point in between, let's call it as C, where they are saying h is maximum height by 2 and here your speed is Vc. So we have to find these values. Now how can we do? Directly, if you see A and B, we can say at A point and B point, total energy Ke plus U is constant, so we will say kinetic energy at A plus potential energy at A is equals to kinetic energy at B plus potential energy at B. Kinetic at A plus potential energy at A is equals to kinetic energy at B plus potential energy at B. Now what is the kinetic energy at A? You are seeing that it is having a speed, so half mv naught square. What is the potential energy? You can see it is at reference level or ground, it is 0. Now when you go at the maximum height, means you cannot go further, so your speed becomes how much? 0. So kinetic energy becomes 0 and potential energy is what? Mg h max, because you are at maximum height, so your energy, potential energy will be mg h max. So from here, if you cut you get the same formula which we get for motion under gravity also, v naught square by 2g. So this is the first part of the question where you find the h max value. Now second thing they are saying the speed at half the maximum height. So if you want to find the speed at half the maximum height, what you can simply do is, once we get the value of h max, now you can write the same equation for A and C. Now for second part, if I take A and C, or you can take C and B, whatever, you will get the same answer. A and C if you write, so at A you will write the kinetic energy as half mv naught square, potential energy 0, at C you will write half m vc square, and plus potential energy you will write mg h max by 2. That's it. So now if you substitute, just see from here what is mg h max equals to. Look at here, mg h max is equals to half mv naught square. Mg h max is equals to half mv naught square, so that means mg h max by 2, can I write it as 1 by 4 mv naught square. Mg h max is half mv naught square, so mg h max by 2 will be a 1 by 4 mv naught square. So put it this side. So half mv naught square minus 1 by 4 mv naught square becomes 1 by 4 mv naught square, and this side you are left with half mvc square. M cancels, 2 cancels, so you get Vc as V naught by root 2. Vc equals to V naught by root 2. So from here, when you equate any 2 points for their energies, you get the expression and you get the value of height, speed, whatever is asked. Is it clear? So it all depends on what is being asked, which equation you have to use. Is it clear to all of you? Okay, so this was one question where we took the case of gravity. Now let's take another question where we have a spring and a block. Now let's see, for that we have this is a spring, this is a block, the spring has been pulled by a distance x from its natural length and block is released from here. So this position you are seeing, the spring has been pulled and the block has been released. So question again is, find number 1, maximum speed attained by the block, And number 2, elongation or compression in the spring when block is moving at half its maximum speed. Try to understand. Here you have pulled the block and released it. When we use the word release, what does that mean? Does the block have any speed or is it at rest? Please reply fast. When I say that the block is released from here, is it having any speed or is it instantly or momentarily at rest? What will you reply to this? It is at rest. When we use the word release, means your speed at that instant is 0. Okay. So here when they use the word release, that means it is at rest. So this release word means speed is 0. Now they are saying the maximum elongation or compression, or when the speed is half of maximum speed, what is the elongation or compression? What I said is, if you see the mechanical energy, which is kinetic energy, who will have kinetic energy? There are two things in the system, one is block and one is the spring. Block will have kinetic energy, and what will the spring have? Potential energy. So total mechanical energy is kinetic energy of the block plus potential energy of the spring. Now here we know the formula of this, it is half kx square, which I told, and for kinetic energy you know is half mv square. So that means if speed is maximum and this total energy is constant, because only which force is taking part? Spring force, which is conservative. So now if V is maximum, means we can say kinetic energy is maximum. If kinetic energy is maximum, this means, can I say potential in the spring will be minimum? Can I say so? If speed is maximum, kinetic energy is maximum, and if kinetic energy is maximum, the sum of two numbers is constant. So if one will be maximum, can I say that the other will be minimum? So if the other is minimum, half kx square, what is the minimum value of half kx square? The minimum value of half kx square is 0, because half kx square cannot be negative. Half kx square cannot be negative, so its minimum value is 0. So now if you see the first case, they are asking maximum speed attained by the block. So I can say initially kinetic energy plus initial potential energy is equals to, when kinetic energy is maximum, potential energy will be minimum. So I can equate the energies. Now from here, what is the initial kinetic energy? They have said that the block was released. When the block was released, then kinetic energy was 0. When the potential energy is asked, it was pulled by x. What is the initial potential energy? Half kx square. When you see maximum kinetic energy, you can write it as half mv max square. And what is the minimum potential energy? Minimum potential energy is 0. So when I equate these two, so I get the value of V max. You can see half cancels. So here V max becomes x times under root k by m. X times under root k by m. And last, second part, they are asking, when the block is moving at half its maximum speed, what is the potential energy? So again we can use this. If I see initial kinetic energy plus initial potential energy is equals to, suppose I see at any instant this Ke final plus U final. Again initial kinetic energy during release was 0. Initial potential energy was half kx square. Now kinetic energy final when it is moving at half the maximum speed, half m maximum speed which we just found, Vmax by 2 square, and they are asking final elongation or compression. I can write it as x final square. So from this equation, if you substitute the value of Vmax over here, then you will get x final. You got x final, sorry, you got Vmax over here from first one. If you substitute the value of Vmax over here, you will get the value of x final. Understood? So this is how we use conservation of energy in question. So initially it was at rest. At any position, if they ask you speed or the elongation, you can use kinetic energy plus potential energy is constant. By this you will get whatever is asked. Clear? So that will be all for today's class. I hope you got what we discussed over here. Kindly remember them. Thank you.
Good morning, students. So yesterday we have discussed about some common names and degree of unsaturation. Now in degree of unsaturation, I have given two questions. How many student remembers that I have given two questions to draw all the possible structures? First question I have given, I think, for C5H10. Draw all possible structures of C5H10. This question I have given. So how to draw these structures? First we have to find degree of unsaturation. Tell me what is degree of unsaturation for this compound C5H10. For C5H10, how to find number of carbon atom plus 1 minus hydrogen divided by 2. So this degree of unsaturation comes out to be 1. Okay. So degree of unsaturation 1 means either one double bond is present or either one ring is present. Means we have to draw structures for alkenes and one cyclic ring structure. So let us start from double bond. If we take 5 carbon atoms in straight chain, so double bond can be present at first position. Next, if we take double bond can be present at second position. So only these two. If you write at third, this will be only second. So only two possible, pent 1 in and pent 2 in. Next, if we take 4 carbon atoms in straight chain and one methyl branching. Now where double bonds are possible? At this position. Next, at this position double bond is possible, and one is at last carbon, this one. Here double bond is possible. So if you check in alkenes, how many structures are possible? 5 structures are possible for alkene. Now this double bond is completed. Now we have to draw for one ring. Ring can be of 5 carbon atoms, so we can take 5 carbon atoms are present. Next, it is not necessary every time 5 carbon atoms are in ring. So it is 4 carbon atom ring and one methyl branching is present, CH3. Next possible case is 3-membered ring is present, and how many methyl will be present? 2. So both methyl are present at same carbon, that is 1, 1. Or next is 2 methyl can be present at first position and second position, 1, 2. These are possible. And there is one more possible case. If we take 3 carbon atom, instead of methyl substituent, we can write ethyl also, C2H5. So total how many cyclic isomers are possible? 5 cyclic isomers are possible and 5 open chain alkenes are possible. So what is answer for this question? That total number of structures are 10. So how many possible structures for C5H10? There are 10 total structures. So what is answer? Total structures are 9. Now next question what we have given, that draw all possible structures of C4H6. Now this is good question, because last two questions which we have discussed, first we have taken in C4H8 which I have solved. Next I have taken C5H10. Their degree of unsaturation is 1. Now what is given? C4H6. So when you solve this C4H6, you will get that degree of unsaturation comes out to be 2. So degree of unsaturation 4 plus 1, 5 minus 6 divided by 2. So what is degree of unsaturation? 2. So in degree of unsaturation 2, there are different cases. First case is either one triple bond is present. Second case is either two double bonds are present. Next case is one double bond plus one ring is present. And another case is possible where two rings are present. So these are possible cases for degree of unsaturation 2. Clear? Either triple bond, one triple bond, two double bonds, one double bond plus one ring, or two ring. So we have to make all possible structures. So let us start from one triple bond. 4 carbon atoms are present. So 1, 2, 3, 4. Triple bond is present at first position. Next case is 4 carbon atom, triple bond is present at second position. If you take this one, 3 carbon atom, and this one, you cannot arrange anywhere triple bond, because maximum valency of carbon is how much? 4. We cannot write triple bond in this structure. So that's why this is not possible. So only in straight chain we can write triple bond. So all this triple bond is completed. Next we have to write for two double bond. So 1, 2, 3, 4. Double bond is present at first position and second position. Next is double bond is present at first position and third position. So only these two are possible cases for two double bonds. So first is triple bond, one triple bond. Next case is for two double bond. Next we have to write for one ring and one double bond. This is important. So if we take 4 carbon atoms, so 4 carbon atom ring, at any position what is present? Double bond. Next, ring can be of 3 carbon atom also. So let us say here methyl is present, CH3. So double bond is present at where methyl is present. Next is CH3, what is present? On next carbon double bond is present. Next case is double bond is present outside the ring. Here what is present? CH2. So in all these cases, if you check, there is one ring and one double bond present. Either 4-membered, one double bond at any position. Next is 3-membered double bond is present at position where methyl is present. Next is double bond at next carbon to methyl. And next is double bond is present outside the ring. So these are 4 cases possible for one ring plus one double bond. And next is 2 rings. So if we check 4 carbon atom, how many rings are present? This is first ring, this is second ring. These type of compounds are called as bicyclo compounds. Clear? So now find total how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is answer for this? Answer is total 9 structures. Okay. So these are important. In this type of one double bond and one ring, we can forget to draw these 3 structure, and one is 2 possible rings. Okay. So these 2 questions I have given in last class. So this is application for degree of unsaturation. And this degree of unsaturation is so much useful when we start now today isomerism topic. So let us start with isomerism. So next topic is isomerism. So this is an important topic for organic chemistry. Now who will tell definition of isomerism? You have studied this in class 10th also. So what you have studied in class 10 will just simply modify from that definition. First you will tell what you have studied in 10th class. What do you mean by isomers or isomerism phenomena? But if we write complete definition of isomerism, what is different? Same molecular formula but different, either structure will be different or arrangement of atoms in 3D space will be different. So if you have to write complete definition, what we have to write? Different structure or different spatial arrangement of atoms. And in simple way we can write, if there are 2 compounds whose molecular formula is same but at least they have difference in one physical or chemical property, those compounds are called as isomers. Clear? So we will write very simple definition for this isomerism, that 2 or more compounds having same molecular formula, but having at least one difference in physical or chemical property. Difference in physical or chemical property are called as isomers. So it includes all type of isomerism. If we write only structure, then it is only structural isomerism. And if we write two compounds have same molecular formula and they have at least one difference in either physical property or either chemical property, they are called as isomers. Or we can say that having different same molecular formula and different structure, or you can say different arrangement of atoms in 3D space, that we have to add extra point. And if you write this, that is sufficient. Now next is, whenever we take isomers, isomers have same molecular formula as well as same empirical formula. Empirical formula means simplest formula or simplest ratio of atoms. And if molecular formula is same, degree of unsaturation is also same, and next is vapor density is also same. So what we write, isomers have same molecular formula. These question will be asked in objective, that isomers has which thing same. So we'll write same molecular formula, empirical formula, degree of unsaturation, and one another thing is vapor density. So if you have not heard about vapor density, simple formula for vapor density of gases is molecular mass divided by 2. So if molecular mass is same, it means vapor density is also same. So whenever we write for isomers, these all things are same: molecular formula, empirical formula, degree of unsaturation, and one is vapor density. So this is simple definition for isomerism. Now, what is vapor density? Vapor density is a relative density. If you have to write formula for this, it is density of gas divided by density of hydrogen, H2. And it can be written as molecular mass of gas divided by 2. So if two compounds have same molecular formula, their molar mass will be same. If molar mass is same, molar mass by 2, vapor density is also same. Clear? So remember this, vapor density is type of relative density. In physics, fluids chapter, we have heard about specific gravity. So specific gravity is defined for solids and liquids, and vapor density is defined for gases. Relative terms have no units, they are unitless quantity. So vapor density is unitless. Now next, if we write how many types of isomerism we have to study, we'll classify isomerism into two parts. And the first part is structural isomerism, which is also called as regioisomerism. Regioisomerism. And second part is stereoisomerism, which is also called as space isomerism. Now, in case of structural isomerism, compounds will have same molecular formula, and same different structural formula. Means arrangement of atoms in bonds will be different. Different type of bonds are present. So what we write here, same molecular formula, but having different structure. Now different structure means different type of bonds are present. That will be called as structural isomerism. And what about stereoisomerism? Same molecular formula and same structural formula. Structural formula is also same, it means bonds are same, but different arrangement of atoms in 3D space. Atoms in three-dimensional space. Because geometry of molecule is three-dimensional. So in three-dimensional, what is possible? Different arrangement of atoms is also possible. Okay. Students are asking, what is empirical formula? For example, if you take compound C2H6, this is molecular formula. Now, what is simplest ratio? It is 2:6 is not simplest. Simplest is 1:3. So, what is empirical formula? It is CH3. So, what is meaning of empirical formula? Simplest ratio between atoms. So, 2:6 is not simplest. Simplest ratio is 1:3. So, this is empirical formula. Now, there are different types of structural isomers. So, how many types of structural isomerism we have to study? First one is chain isomerism. Next is position isomerism, functional isomerism. Next is metamerism. Next one is ring chain isomerism. And last is tautomerism. So in these foundation classes, we will study first four part. These are more important. Tautomerism is also important, but in this part of study, when we are doing foundation classes, we will only study chain, position, functional and metamerism. And if we write for stereoisomerism, it is of two types. One is geometrical isomerism and one is optical isomerism. Okay. So there are these types of classification are for structural isomerism, and geometrical and optical are types of stereoisomerism. So this is only the names that how many types of isomerism we have to study. So before starting from structural isomerism, chain, position, functional, metamerism, first important we have to remember that how many isomers of alkanes are possible, how many isomers of alkyl group are possible. So if we remember that number of isomers of alkane and alkyl group, it is very easy to solve total number of structural isomer. So let us first start with isomers of alkane. Isomers of alkanes. Only structural isomers we will discuss. But we discuss here only structural, means having different structure. Now students, you have to tell how many minimum carbon atoms are required in alkanes so that structural isomerism will exhibit. Minimum number of carbon atoms are required to exhibit structural isomers in alkanes. How many are required? 4 carbon atoms are required. So if we take first example, molecular formula is C4H10. How many possible cases are there? 2 possible cases. 4 carbon atoms in straight chain, 3 carbon atoms and 1 branching. Now tell me name of first one. What is common name of first one? Very good, butane. Do not write butane, but we write normal butane. What is common name for second structure? What is common name for this? Isobutane. What is common name for this? Isobutane. 2-methyl propane is IUPAC name. Common name is isobutane. So how many structural isomers are possible for C4H10? 2 structural isomers are possible. Clear? Now next we have to write for C5H12. Try to draw how many isomers of C5H12 are possible. 3 can be possible. In pentane there are 3 possible cases: normal pentane, isopentane and neopentane. Now how to draw these structure? First we can write 5 carbon atoms in parent chain, straight chain. Next we can take 4 carbon atoms and 1 methyl branching. Now methyl branching is only possible at second position. Both are second. This and this are second position. Next is 3 carbon atoms in straight chain and 2 methyl branching at second position. So what is name of first one? This is called as normal pentane. Second is called as isopentane, and third is called as neopentane. These are common names for the structure, neopentane. So how many isomers are possible for C5H11, H12? 3 structural isomers are possible for C5H12. Now next is important, C6H14. How many structural isomers for C6H14 are possible? So what is possible case here? How to draw? 3, 4, 5, 6. All 6 carbon atoms are in straight chain, first part. Next is 5 carbon atoms in straight chain. At second carbon, methyl branching is present. Next is methyl branching is present at second position. This we can also do. Next case is 4 carbon atoms in straight chain. How many carbon atoms? 4. Now how many methyl branching are present? 2. Both methyl branching is at second position. Or 1 methyl at second position, 1 methyl at third position. So how many isomers are possible? Structural isomers? 5 are possible. So for C6H14, 5 structural isomers are possible. Now these you have to listen carefully, because in exam, if this question will come, if you do not remember that 5 are possible, so in exam maximum times you will get 1 isomer less. So answer will get 4. Now you will forget this, that 2 methyl can be present at second position and at third position. So for C6H14, how many isomers are possible? 5 structural isomers are possible. Next is C7H16. Now how many isomers are possible for C7H16? Try to attempt. Now this is important, some structures will forget to draw in this, you will get less than 9. Answer is 9. So first is all 7 carbon atoms in straight chain, 1, 2, 3, 4, 5, 6, 7, and write down in sequence. There is no general formula. Up to 7 carbon atom you have to remember, from 4 carbon atom to 7 carbon atoms. So first is 7 carbon atoms in straight chain, and it is easy to draw. Next is write down 1, 2, 3, 4, 5, 6. Methyl branching at which position? Second position. 5, 6. Methyl branching at which position? Third position. Now if you move to next carbon, this is also third. So only these two are possible in 6 parent chain, 1 methyl branching. Next we will take 5 carbon atoms in straight chain, and how many methyl branching? 2 methyl branching. So both methyl are present at second position. Next we can write both methyl are present at which position? Third position. Next we can take 2 methyl on different position. One is second, one is third. Now one is second and one is fourth. Second, fourth. Next we can take 4 carbon atom and how many methyl? 3 methyl. So 2 are present at second position, 1 is present at third position. Now these 8 structures you can easily draw. 1, 2, 3, 4, 5, 6, 7, 8. But 9th is different. In 9th, if we take 5 carbon atoms and 1 ethyl branching can also be possible. So this is important. Every time you will forget this structure. So what is present here? 5 carbon atoms in straight chain, and at third carbon which substituent is present? Ethyl. In all other isomers, substituent is methyl, but in this case substituent is ethyl. So total how many isomers are present? 9 structural isomers are possible for C7H16. Now what is conclusion for this complete alkanes part? So this conclusion we have to remember. For alkanes, it start with 4 carbon atoms, C4H10, next is C5H12, C6 H14, C7H16. Only these four we have to remember. How many isomers for C4H10? 2 isomers. For C5H12, how many isomers? 3. C6H14, how many isomers? 5. For C7H16, how many isomers? 9. So you can remember this sequence 2, 3, 5, 9. That is sufficient. Why cannot we place ethyl substituent for second carbon? 3, 4, 5. Now if you take, this is parent chain. Now 5 carbon is not parent chain. 6 carbon atom is parent chain. At third carbon methyl is present. That we already drawn. So that's why this structure is not possible. At second methyl we cannot write. So this sequence you have to remember 2, 3, 5, 9. These are isomers of alkane. Very important. Next we have to find out structural isomers of alkyl group. Structural isomers of alkyl group. How alkyl group is formed? Now alkyl means if we remove one hydrogen atom, not alkyne, alkyl group. One hydrogen atom if we remove from alkane, what we get? Alkyl we get. So first we will take isomers of C3H7. Now how C3H7 is formed? It is formed by removal of hydrogen from C3H8. Remove one hydrogen. So what we get? C3H7. Now how many possible cases are there? If we draw structure of C3H8, propane, only this structure is possible. CH3, CH2, CH3. Now if we write hydrogen is removed from last carbon, that is from first carbon. So this compound is formed, this alkyl group. And if we remove hydrogen from second one, so this is formed CH3, CH, CH3. Now students, you have to tell what is common name for first alkyl group and what is common name for second alkyl group. We have written common names for alkyl group. Now tell me name of first alkyl group common name. First one is normal propyl and second one is called as isopropyl. Clear? So if they ask how many structural isomers of C3H7 are possible, so how many structural isomers are possible? 2 structural isomers are possible. Similarly, we can draw for C4H9 also. If I write for C4H9, now for C4H9, first thing is if we take CH3, CH2, CH3. First, if I remove hydrogen from any of the end carbon, this is formed. If I remove hydrogen from second carbon, CH, CH3, this will get. Next is isobutane is also possible for C4H10. Now 2 possible cases are there. If we remove hydrogen from the last carbon, CH2, and one is if we remove hydrogen from tertiary carbon. So total how many isomers are possible? 4 isomers are possible for C4H9. And what are their names? This is called as normal butyl. This second one is called as secondary butyl. Third one is called as isobutyl. And this last one is called as tertiary butyl. And if you do not remember these common names, you can see last to last lecture, I have written all these common names, how to draw normal butyl, secondary butyl, tertiary butyl and isobutyl. Okay. So total how many isomers are possible for C4H9? 4 structural isomers are possible. So in this complete isomerism, what we have to remember? Conclusion for isomers of alkyl. isomers of alkyl, that is structural only. So remember this sequence: 2, 4, 8, 17. What is sequence? 2, 4, 8, 17. Now 2 is for C3H7. 4 is for C4H9. 8 is for C5H11 and 17 is for C6H13. But more important are 2, 4, 8. So this sequence you have to remember: 2, 4, 8, 17. For first alkyl C3H7, because alkyl isomers start from 3 carbon atom. So 2 isomers, normal propyl, isopropyl. And for 4 carbon atom, 4 are possible. What is possible? Normal butyl, secondary butyl, isobutyl and tertiary butyl. For 5 carbon atom, how many are possible? 8. And for 6 carbon atom, how many possible? 17. If you move to next 7 carbon, there are 39. So that is not possible. So only maximum time what you get: 2, 4, 8 up to 5 carbon atom. So we have to remember this for alkane and alkyl. I will show you which conclusion we have to remember. First this conclusion for alkane: 2, 3, 5, 9. There. Next is for alkyl. What sequence we have to remember? 2, 4, 8, 17. 17 you can leave. If you remember 2, 4, 8, that is also sufficient. So today we have discussed basics of this structural isomerism. So in next class we'll start from chain isomerism and position, next functional metamerism. So all different type of structural isomerism we'll study, and then we write combined question how to find total number of structural isomers. Okay. So students, thank you for today.
Hi students, good morning. Today's our botany class is nucleic acids part 2. In last class you have learned basic information of DNA. Now the detailed structure of DNA, detailed account of DNA molecule. Before going that one, a small review or recollection of concepts of the last class. Try to answer for the following questions. Nucleoside, or the chemical constituents of the nucleoside, or the chemical constituents of the nucleoside. Side, not tide. Yes, sugar molecule and nitrogen bases. Good. What type of sugars are found in nucleic acids? Type of sugar molecules in nucleic acids. Name of the sugar. Is it deoxyribose sugar or ribose sugar? Deoxyribose or ribose? If the nucleic acid is the RNA, then sugar is the ribose. If the nucleic acid is the DNA, the sugar molecule is the deoxyribose. Yes. Jayasri, good. Pentose. Both are example for pentose sugars. Both are example for pentose sugar molecules. In both the sugars, number of carbons are 5. 5 carbon, penta. Suffix for sugars, ose. O suffix for sugars, pentose. 5 carbon contains sugar is pentose. DNA, D for deoxyribose. RNA, R for ribose. Next, what kind of nitrogen bases are found in? What kind of nitrogen bases? In DNA molecule, 4 types of nitrogen bases such are A, T, G, C. Whereas in RNA, also 4 types of nitrogen bases are present such are A, U, G, C. 4 types of nitrogen bases in DNA: A, T, G, C, RNA, A, U, G, C. Once recollect full forms of the A, T, G, C. A for adenine, T, thymine, G, guanine, C, cytosine. In case of RNA, uracil is found instead of thymine. So what kind of nitrogen base is the unique from DNA to RNA? Thymine, uracil. Remaining all are similar. These nitrogen bases are 2 types, purines and pyrimidines. Adenine, thymine are purines. Guanine, adenine, guanine are purines, thymine, cytosine and uracil are pyrimidines, PY, pyrimidines, PU, purines. Now, these are the concepts learned in last class. Next question, the number of nitrogen bases types common between RNA and DNA. Common type of bases in both RNA and DNA types, I am asking about the number. Yes, 3 types such are A, G, C are common. No, third option, second option only. Types 3, adenine, guanine, cytosines are common. Next, one more question. This is the nitrogen base not associated with RNA molecule. What kind of nitrogen base not associated with RNA molecule? Not associated with RNA, thymine. Not associated with DNA, uracil. Yes, yes, good. Next question, chemical formula of deoxyribose sugar. Okay, good. Next, chemical formula of deoxyribose sugar. Pentose, 5 carbons. 1 oxygen atom is the deficit in ribose sugar, then the sugar is called deoxyribose. What is the meaning for the D? Deficiency of 1 oxygen atom in a ribose. Deficiency of 1 oxygen atom in a ribose, then it is the deoxyribose sugar. Actually, original formula of the ribose sugar is only ribose, C5H10O5. By losing 1 oxygen atom, it becomes as O4. Yes, deficiency of 1 oxygen. Good. Next question. One of the following is not a complementary nitrogen base pair. Not a complementary nitrogen base pair. I think you didn't learn about the complementary base pairing. I think you don't know. I will explain. BLH. Scientist Erwin Chargaff explain the complement relation between nitrogen bases. According to him, number of purines, total number of purines in DNA molecule should be equal to number of pyrimidines. It is called as the Chargaff principle or Chargaff rule. Tell me what explained by the Chargaff rule? Total number of purine molecules in a double-stranded DNA should be equal to total number of pyrimidines. It is one rule. What are purines? A plus G purines equal to T plus C pyrimidines. A plus G equal to T plus C. It is the Chargaff rule or Chargaff principle. It is applicable for double-stranded structures only. The Chargaff rule is applicable for both double-stranded DNA as well as the double-stranded RNA molecule. Not applicable for single-stranded molecules. How can you say? Observe here one small diagram. It is the one strand of the DNA molecule. In one strand of the DNA molecule, adenine is there. In opposite strand, exactly opposite to A, T is there. So, A number is always equal to T. A is the purine, T is the pyrimidine. So, both numbers are equal. For example, in one strand G is there, then what is the nitrogen base should be present in opposite strand? C. Hence, we can say both GC are complementary pairs, A and T are complementary pairs. AT, a complementary pair, GC, complementary pair. This kind of pairing is possible in double-stranded structure only. Suppose the second strand is not there, second strand is absent, at the time this kind of pairing is not at all possible. Likewise, I will give a sequence of nucleotides one strand. You have to find out the sequence of nucleotides or nitrogen bases in opposite strand. T, C, G, A, T. Now tell me, what is the sequence of nucleotides or nitrogen bases in second strand? Can you fill these blanks or gaps? What is the complementary pair for the T? What is the base pair for the T? Paired nucleotide. Yes, A, good. For C, yes, good, G. For G, C. For A, again T. For T, A. Yes. In case of RNA, in place of the T, uracil is there. So AT and GC pairing is there. Finally, we can conclude A number always equal to T, G number always equal to C. A number equal to T, G number equal to C. A plus G purines equal to T plus C pyrimidines. It is a Char-Graph rule or Char-Graph principle applicable for both double-stranded DNAs and double-stranded RNA molecules. Is it possible or not to find out the sequence of nucleotides in one strand of the DNA molecule by knowing the sequence of nucleotides in other strand of the DNA molecule? To find sequence of nitrogen bases in one strand of the DNA by giving one strand. Yes, exactly. Possible. By knowing sequence of nucleotides in one strand, is very clear, easily form the sequence in other strand. Once give the answers. What is the complementary base pair or basis for this T, C, A, G, C, T, A? If the sequence is given as a question in examination, we can fill sequence of nitrogen bases in opposite complementary strand. For T, A, for C, G, for A, T, for G, C, for C, G, for T, A, for A, T. So A, G, T, C, G, A, T is a sequence of nucleotides in another strand. Okay, good. A, G, T, C, G, A, T. Yes. What is the relation between these two strands? Relation between these two strands, complementary strands. Both the strands are complementary. Both the bases are complementary. AT complementary, GC complementary. All these things are applicable or not applicable for RNA. Yes, when RNA is in double stranded structure, then Char-Graph rule is applicable. Usually RNA molecules are single stranded. At the time, Char-Graph rule is not applicable. Char-Graph rule is not applicable. Not applicable. Char-Graph rule is applicable for DNA, not for RNA, when RNA is in single stranded condition. But here one thing, mostly RNA molecules are single stranded. Mostly RNA molecules are single stranded, that's why Char-Graph rule is commonly not applicable. Okay? By using such concepts or knowledge, try to give answer for this question. One of the following is not a complementary nitrogen base pair. Yes, third option. AT is the pair, GC pair, CG pair, but AC is not complementary base pair. Yes, good. Next question. The backbone of DNA polynucleate strands is formed by the alternative arrangement of. Later I will explain this concept. The backbone of the DNA polynucleated strand is formed by the alternative arrangement of. Read the options and try to give one proper answer. Phosphate, sugar, nitrogen base, wrong option, gone. Phosphate and nitrogen base, it is also wrong option. Sugar and nitrogen base, it is also wrong. Yes, first option right answer. Phosphate and sugar molecule. It is a sugar molecule. One more sugar. Sugar. Phosphate, nothing but phosphoric acid. Ester bond. Are linked with to form a long chain. Now it is known as the backbone. In this backbone, nitrogen bases appears like a steps or lateral side of the backbone. NB means nitrogen bases. Nitrogen bases appears like a steps laterally on this backbone. So backbone of the DNA is made up of sugar, phosphate alternately. S for sugar. Phosphate. Sugar, phosphate at the backbone of DNA. This is a DNA backbone. sugar phosphates. Nitrogen base should not include in backbone. Nitrogen bases are appears like just lateral side chains. First of all, I will explain some content. Later, try to give answer for this one. I will draw one small structure. Try to guess what is the name of the structure. What is the name of this molecule? In it, it is the first carbon, second carbon, third, fourth. This is the last carbon. A sugar molecule. Sugar. Name the chemical constituent is bind to the first carbon of the sugar. Nitrogen base. Now both base and sugar together called nucleoside. What kind of chemical compound is bind to fifth carbon of sugar molecule? Phosphate. The bond present between phosphate to fifth carbon, phosphoester bond, first carbon of sugar to the nitrogen base, glycosidic. Now the three together called as nucleotides. Nucleotide number 2, number 3, 4, 5, 6, like that several nucleotides are found in polynucleotide chain. Polynucleotide chain. Now listen, now it is very essential. 2 minutes class is very essential, be careful. How does one nucleotide linked with another nucleotide? How does one nucleotide is joined or linked to another nucleotide? What kind of bonds are helpful for joining of all these nucleotides? Serially, one after another one. In case of polysaccharides, two adjacent sugar molecules are joined by glycosidic bonds, you learned already. In protein molecule, two adjacent amino acids are linked with another one by peptide bonds. So peptide bonds are essential for linking of amino acids. Glycosidic bonds are essential for linking of sugar molecules in polysaccharides. Likewise, what kind of bonding is essential? Linking of one nucleotide to another nucleotide. Phosphoester bonds. Phosphoester bond. Already one phosphoester bond is the existing between phosphate to fifth carbon of sugar molecule. One more phosphoester bond is formed. One more phosphoester bond. That ester bond is possible to present between third carbon of one sugar to the phosphate belongs to another nucleotide. Another nucleotide. Already the existing phosphoester bond, newly synthesized phosphoester bond. One phosphate able to make two types of ester bonds. Now both the esters with phosphate together called phosphodiester bond. It is a phosphodiester bond. Likewise, nucleotide number 1, nucleotide number 2, it is a nucleotide number 3. How does the third nucleotide bind to the second nucleotide? Making of one more phosphoester bond. A phosphate with two esters is the phosphodiester. Fourth one, phosphoester, second ester, phosphodiester. Phosphoesters with another esters. Okay. Now this chain is called polynucleotide chain. Many nucleotides are linked with another one to form a long polymer, that is a polynucleotide. We can write that entire chain with a single line. It is a polynucleotide. In this line, each and every dot is the representative of one nucleotide. Nucleotide 1, 2, 3, 4, 5th one, 6th one, 7th one, 8th one, 9th one, like that. So many nucleotides are there. This entire molecular structure we can write as a single line with dotted lines. Okay. Each and every dot is the representative of one nucleotide, or it is a backbone of the DNA. The nitrogen bases are found as a side chain on this backbone. A, T, G, C, C, A, G, T, C. The sequence of nucleotides is different from DNA to DNA molecule. The DNA is also different from person to person or organism to organism. It is about the one strand, but DNA is the double stranded structure. Likewise, you have to write one more structure of the polynucleotide strand. Guess now, what is the name of this structure? Find out. It is also sugar molecule. It is a sugar molecule. One nitrogen base attached to first carbon of sugar, second carbon, third carbon, fourth carbon, oxygen is the fifth carbon. Phosphate is present here. The bond between fifth carbon of sugar to the phosphate is the phosphoester bond. Base to first carbon of sugar is the glycosidic bond. Second nucleotide, third nucleotide, nucleotide number 4, nucleotide number 5, number 6. Like that, so many nucleotides are there. It is the one strand of a DNA molecule. This is the second strand. Like first strand, in second strand also phosphodiester bond linking is essential. This phosphate bind to third carbon of sugar, phosphate to third carbon, or third carbon to phosphate, third carbon to phosphate, third carbon to phosphate. These are the two strands of the DNA molecule. One strand is in vertical, second strand is in inverted position. Second strand is in inverted position. Another one more minute is very essential. Concentrate. In this entire strand, this is the end is the last carbon or fifth carbon. But opposite end of this chain is third carbon. Even in polypeptide strand, one end is called N terminal, opposite end is the C terminal. Likewise, polynuclear strands also differentiable into two polar ends. One is the 5' end, another one is the 3' end. What is the meaning for the 3' end? At one end of the DNA, the last carbon of the sugar molecule is the third one, and it is ready to make a new bond with newly incoming nucleotide. If any kind of new nucleotide is added to it, that should bind to the third carbon, and this is the end is called 3' end, or the last carbon of this end is the third carbon. That's why it represented with the 3' end. Opposite is the 5' end, because the last carbon in this end is the fifth carbon. So one end of the polynucleate strand is the 5', another end is the 3'. Likewise, study the second strand also. What is the name of this end? This is the end ends with 3' end. Here it is the 5' end. So both the strands are in opposite directions. One strand is in 5' to 3', another strand is in 3 to 5'. It is the opposite directions. Both the strands of DNA molecules are opposite in direction. Observe in this diagram here. This is the second strand of the DNA molecule. In this strand, one end is the 3', another end is the 5'. So what kind of relation is there? Both the strands, both are complementary and both are parallel, but anti-parallel arrangement is there. Anti-parallel arrangement. Observe here. For example, the one strand. One end is the 5', this top end is the 3', whereas in second strand, reverse manner is there. Both are parallel. But here 5' end is the top, 3' end is the another one, down. Okay. In this strand, it is the 5', 3'. Whereas in bottom, it is the 3, it is the 5. Opposite direction is there. Clear? Are you getting an idea? Any doubt here? So what kind of relation is there both the strands? Parallel or anti-parallel? Yes, anti-parallel. Anti-parallel. How can you say both the strands are in anti-parallel? If one strand is in 5' to 3 direction, opposite strand is in 3 to 5 direction. That is meaning for anti-parallel. Likewise, another interesting thing, observe here. I will write a sequence of nucleotides in one strand. A, G, C, T, A, T. Now you can able to write the sequence of nucleotides in another strand according to the char graph rule. According to char graph rule. Try to give complementary base pairing. What is the complementary base for the A? If A is found in one strand, what is the base is in another opposite strand? T. For G, C. For C, G. For A, complementary base. For T, complementary base is A. If the nitrogen base is A, complementary one is the T. For T, A. How does one strand bind to another strand? By forming hydrogen bonds. Between A and T, two hydrogen bonds are formed, double bond. These are hydrogen bonds. Earlier somebody asked, what kind of bonding is there between the two strands of DNA? Answer for that question is the hydrogen bonds. Hydrogen bonds. Between G and C, triple bond is there, triple hydrogen bond. Even CG also, triple bond. TA, double bond. AT, double bond. TA, double bond. Yes, between AT, double hydrogen bond, between GC, triple hydrogen bond. Now tell me, total how many types of bonding is there in double stranded molecular structure of the DNA molecule? Total how many types are there? And types, first one is the glycosidic, second ester bond, third one hydrogen bonds. Three types are possible. Within a single strand, only glycosidic and ester bonds are there. Whereas in double strand, second strand is also there, then only hydrogen bond formation is there. You can write the same sequence here also. What is the base pair sequence in opposite strand? T, A, C, G, G, T, C, A, G. Both are binded with hydrogen bonds, such are either double bonds or triple bonds. If the AT pair is there, double bond, GC pair, triple bond. So this is the detailed account of molecular structure of DNA molecule. Detailed account of molecular structure of DNA. One strand, opposite complementary strand. Both the strands are anti-parallel. Both the strands bind with each other with the help of hydrogen bonds. Without nitrogen bases bond, hydrogen bonding formation not at all possible. By using such idea or knowledge, try to answer for this question. Read carefully. Phosphodiester bonds are present between the sugar and nitrogen base bond is a glycosidic, not phosphoester. So first option wrong. Two nitrogen bases are the opposite strands. Hydrogen bonds are there, that's why it is also not. Between two adjacent nucleotides of the same strand, phosphodiester bonds are there. Yes, good, very good. Third option is right answer. There is no any kind of bonding between phosphate nitrogen base. No bonding. What kind of bonds are there? Two nitrogen bases of the opposite strands. Here hydrogen bonds. Sugar and base, glycosidic bond. So, nature of bond linking. Glycosidic bonds are bound sugar and nitrogen. Hydrogen bonds are found in two nitrogen bases of the opposite strands of the DNA molecule. Between two adjacent nucleotides of the same strand within the single strand, phosphodiester bonds are there. Okay, good. Next question. In DNA helical structure, cytosine base is paired with guanine by DNA helixes. C bind with G by how many bonds? Yes, first option, 3 hydrogen bonds. In case of AT, 2 hydrogen bonds. Next, one more question. The similarity between the DNA, RNA is that both the similarity between the DNA and RNA, both are polymers of nucleotides. First option wrong answer, because DNA is a double stranded usually, RNA is a single stranded. Some exceptions are there, but usually, more commonly, DNA double stranded, RNA single stranded. That's why first option is wrong. Have the similar sugars, no, deoxyribose sugar in DNA, ribose sugar in RNA, it is also wrong. Have similar pyrimidines, no, in DNA, thymine, whereas in RNA, uracil is there, that's why fourth option is also wrong. Only one R are polymer of nucleotides. Both are polynucleotide strands. DNA, RNA are example for polynucleotides. Okay, good. Number of hydrogen bonds between A and T, very easy question, second option. I will draw one small diagram and guess what is it. It is the diagram of, identify this diagram, guess it, just double stranded ladder, but according to Watson and Crick, DNA is a double stranded, no doubt, but double helical structure that appears like a twisted ladder. By twisted ladder, then we can draw the double helical model of the DNA likewise. Both the strands are helically coiled with each other to form a twisted ladder like model. The name of this model is double helical model. Double means two strands coiled with each other. That's why it is a double helical model. This double helical model structure of the DNA proposed by both Watson and Crick. In the two strands is the one first base pair, second base pair, third one, fourth one, fifth one, sixth, seventh, eighth, ninth, 10th. Now this is the one helix. In each helix, how many base pairs are there? 10 base pairs are present. Even in second helix also 10 base pairs are there. Base pair 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In third helix also another 10 pairs are there. Pair 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. From here to here one helix or one coil. It is also one more coil. It is also one more coil. Coil, helix, torn, all are similar words. In each helix, number of base pairs are 10 BP. Our number of nucleotides are 20. 20 nucleotides are there. Our base pairs are 10. 10 base pairs equal to 20 nucleotides. 10 base pairs equal to 20 nucleotides. The length of this DNA molecule from here to here, the length of entire coil is 34 angstroms. 34 angstroms. Within this 34 angstroms length, 20 nucleotides are there. 20 nucleotides equal to 10 base pairs. Then we can guess the distance between two adjacent base pairs is the 3.4 angstroms. 3.4 angstrom is the distance between two base pairs. Within coil 10 base pairs are there. 10 into 3.4 final length of entire coil or each coil is the 34 angstroms. Getting idea? From here to here it is the one helix. Within the helix 10 base pairs are there. These 10 base pairs are equidistantly arranged. Distance between two adjacent base pairs is 3.4 angstroms. 10 3.4 so 34 angstroms. Identify this diagram here. It is the one helix, nothing but a one pitch. The distance of that pitch or helix is 34 angstroms. We can convert the angstroms into nanometers. 34 angstroms equal to 3.4 nanometers. It means 10 angstroms equal to 1 nanometer. That's why 34 angstroms equal to 3.4 nanometers. Number of base pairs in each strand, each turn or each helix 10. The distance between two adjacent base pairs 34 by 10, 3.4 angstroms, or 3.4 nanometer by 10, 0.34 nanometers. According to double helical model of DNA proposed by Watson and Crick. Okay. Try to remember all these values to solve some kind of questions related to DNA. Okay. Bye, Nan.
So very good morning, students. Last class we discussed fundamental aspects about muscle, skeletal, smooth and cardiac, isn't it? So today we will be focusing mostly on skeletal muscle. How does it look anatomically inside, and which components are allowing it to perform contraction and relaxation. Good? Okay. So as just a recap, a bone this bone was attached with a connective tissue What do you call this connective tissue? Tendon. Yes. Now these tendons were connected to skeletal muscles. Showing with different color. Skeletal muscle. Okay. Now guys, a skeletal muscle, inside a skeletal muscle there are many bundles of tissues, we can say aggregates of cells. So inside skeletal muscle we can see many bundles of muscle fibers present together. These bundles of muscle fibers are called as fascicles. There might be many fascicles. So muscle consists of muscle bundles called as fascicles. Correct. Now in between these fascicles, there is thin connective tissue like this. This connective tissue between fascicles is called as fascia. Tissue outside fascicles, or we can say that the connective tissue which holds fascicles together is fascia, like this. This is fascia. Okay. So fascicles are embedded inside fascia. Now inside each fascicle, if you zoom again, inside each fascicle you can see many muscle fibers like this. So each fascicle consists of many muscle fibers like this. Okay. Label it for me. So fascicles, then fascia, then muscle fibers. This entire thing was muscle. Muscle is attached to bone with the help of muscle is attached to the bone with the help of which tissue? Tendon. That was a tendon. Done. So muscle has muscle bundles, fascicles. Fascicle consists of muscle fibers. Level 1, level 2, level 3. Now, what we do is now, just pull out one muscle fiber like this. Observe here, pull out just one muscle fiber. Pull out one muscle fiber. Guys, from this angle, see, this may look like circle, but if this is a front view from front, but when you turn this, you can see elongated muscle fiber. Same thing is applicable to this structure also, like this. It was a single cell. See guys, it's a single cell because of its very lengthy nature, because of its elongated structure. We refer this muscle fiber, this is single cell. I am telling you, this is a single cell. Because of this elongated nature, we often refer muscle cell also as muscle fiber. So indeed, fibers are actually, what are these? Muscular cells. Okay. So if we zoom into this muscle cell or muscle fiber, a single muscle fiber, it was cylindrical, elongated with no branches, right? You guys remember this? Visible? A single muscle cell, no branches, elongated. Done. And tell me now, how many nucleus shall I show you here? Skeletal muscle is uninucleate, binucleate, or is it multinucleate syncytium? Tell me, is it uninucleate, binucleate, or it is a multinucleated syncytium? Yes, very good. It is multinucleated. So, what is the synonymous term for multinucleated? Syncytium, or you can also call that as senocytic. So, let us show mini nucleus here. Not serolytic Tikshana, it is senocytic. Senocytic. Okay, clear? There were mainly two types of proteinaceous molecules which help in muscle contraction and relaxation. These two proteins, they help in muscle contraction and relaxation. So often we call them as contractile proteins. These contractile proteins, one looks very thin, one looks very thick. So the thin contractile filament, thin contractile protein was called as actin. Actin is thin contractile protein, whereas a thick contractile protein which helps in contraction was thick myosin. These were referred as contractile proteins, myofibrils or myofilaments. It's up to you. So, which is thin? So, thin filament was actin. Actin is a component of thin filament, whereas myosin is a component of thick filament. Done. Actin is thin filament, myosin is thick filament. These are referred as contractile proteins. We refer them as contractile proteins. Okay, this is symbol we use as a shortcut for proteins. Done. Is it clear to this point? Guys, actin is thin filament, myosin is thick filament, okay? And these actin thin filaments and myosin thick filaments are arranged inside muscle fiber in such a way that they will appear as striations or stripes. I'm telling again, thin actin filaments and thick myosin filaments are arranged in such a way that we can see striations or stripes inside a muscle cell. I will tell you fundamental arrangement pattern. Just follow this picture clearly, okay? Let us not go into depth of this because as it is online now, you guys may understand just partial things. But when you come offline, you'll understand the whole thing. See, drawing this again. Guys, the entire concept of muscle cell you learn from pictures, not from bookish theoretical knowledge. Okay? That was a single muscle cell, right? Muscle cell, or call that as muscle fiber, up to you. So plasma membrane of muscle cell was called as sarcolemma. Sarco means muscle. Okay, same time cytoplasm inside muscle cell was called as sarcoplasm. Okay, and this muscle cell was rich in endoplasmic reticulum, mainly in smooth endoplasmic reticulum. Therefore, endoplasmic reticulum inside the cell was often referred as sarcoplasmic reticulum. Okay, and muscle cell consists of numerous mitochondria, and these mitochondria could be referred as sarcochondria. Some books say this. So sarcolemma, sarcoplasm, sarcoplasmic reticulum, and sarcochondria. Names given to cell structures. No new names. Just add a term prefix to whatever you want to say. Sarcoplasm in place of cytoplasm. Sarcolemma in place of plasma lemma. Sarcochondria in place of mitochondria. Sarcoplasmic reticulum in place of endoplasmic reticulum, like this. Okay, now inside this muscle cell, guys, I'm rubbing off everything inside a cell just to make sure that you see only one aspect clearly. See, yes, sarco means muscle, correct? Sarco means muscle, myo also means muscle, Latin and Greek difference. Both sarco and myo, different languages, and both are same as muscle. Just like, guys, you learn about di, bi, both are two. Tetra, quadra, language difference, Latin and Greek, same. Sarco, myo, both are accepted. Okay, so I'm rubbing off everything here to show you how thin and thick filaments are arranged. Okay, not showing anything new. I'm not showing, everything was there, but I'm not showing anything. I'm not showing nucleus or mitochondria, ER, nothing. I'm just showing you thin thick filaments. That's it. Confine to thin and thick filaments. Okay, see this very carefully. To this plasma membrane, attached to it were some proteins. Okay, these proteins are actually attached to an elastic membrane-like protein. I'm telling again, these proteins are attached to an elastic membrane-like protein like this. This membrane-like structure, elastic structure, this membrane-like elastic structure was actually referred as Z line. Okay, and adjacent to Z line you can see a fibrous proteinaceous structure like this. This fibrous structure is referred as M line. Guys, elastic structure was Z line, fibrous structure was M line. Okay, so arrange Z and M lines alternatively. See, again Z, so between Z lines you can see M lines. Focus here. So label it none. So which line this is? Z. This is M. Again Z. Again M. Z. M. Z. Okay. So number of Z lines and number of M lines depend on length of the muscle cell. There are some muscle cells which have got 10 to 15 ZM lines only, and sometimes muscles could be very lengthy. We may have 40 to 50 ZM lines also. Both are possible. You can have small muscles, large muscles, isn't it? The length was never a question. Okay, done till this point. Z line, M line, Z line, M line, Z line, M line, Z. Guys, only if you listen and understand about muscle cell structure, then it will become very easy. It will come in handy to understand about muscle contraction. So structural and anatomical details are very important to learn about actual physiology behind this structure. That's why we always say morphology, then anatomy, then physiology. Even in your textbook also, the syllabus was framed in such a way that morphology you learn first, then go to anatomy. After that we'll start physiology. Okay, is it clear till this point? Focus here, listen to this properly. Z line, M, Z, M, Z, M, Z. Okay, and the rule was that Z lines were attached with thin filaments only, whereas M lines were attached with thick filaments only. Z was attached with thin filament only, whereas M lines were attached with thick filaments only. Done. Z with thin filaments, M with thick filaments. Thin filaments consist of mainly which protein? Actin. Whereas thick filaments mainly consist of myosin. Once you come here, we can discuss in detail about actin and myosin, because that was at molecular level Not now. We need to understand fundamental aspects of a subject. So I'm letting you know very basic outline of the topic. Done. Guys, be very careful with the spelling myosin, myosin, not mycin. Mysin is different thing. Okay, please be careful. And myocin is not acceptable. That will give different meaning at all. It will become an antibiotic. No, myosin, that's it. Okay, so Z lines are attached to thin filaments, M line is attached to thick filaments. Done. Now just see this carefully. I am showing you thin filaments in white color, thick in red. Okay, thin, of course, thin lines, thick, of course, thick lines. So see, thin filament. Done. Thin filament. Again, thin filament. Again comes thin filament. Done. First we'll draw thin filaments only. Done. So thin filaments are attached to either both sides of Z line or only one side of Z, because space was not sufficient here. That was the main problem there. Done. So first show thin filaments. Now comes thick filaments. Increase thickness. As I told you, thick filaments are attached to M lines only. So a part of thick filament was free and not overlapped, whereas some parts are actually overlapped with thin filaments also. For this. Follow this carefully. Okay, done. Again, thick filament. Done. Again, thick filament. So Z lines were attached to thin filaments, whereas M lines are attached only with thick filaments. Could you see this? Is picture clear, guys? We can make it a bit thicker also if you want. You need to understand structural aspects before you can learn about their physiological aspects. That was more important. Without properly learning any of these structural aspects, it is useless, or it will become very difficult for you to learn about functional aspects or physiological aspects. So please focus on structural aspects first. Focus on morphology and anatomy. Then it will be easy for you to focus then on physiology of a muscle. So we learn muscle contraction for sure, but not without this information. Done. Is this picture clear, friends? You could see very clearly Z lines were attached to thin filaments, M lines were attached to thick filaments. Done. Okay. Now observe this. I'm going to zoom in, not zoom out, zoom in. So I'll decrease size of this picture. You are able to see a striated appearance, right? You could see some striations, right? Lines, white line, white line, white line between red lines. Done. So if you zoom out now, then you'll get to know these striations are because of arrangement of thin and thick filaments. Yeah, now that's how it comes. Done? Guys, is it visible? Done with this? So Z line, M line, Z line, M line. Okay. Now, done? So I'm showing you again. Zoom in. See this. There are even more details I can add up. But wait. First you need to see this. Accept it. Then you can learn again. Before fixing something in your brain, you cannot skip to next topic or next point. So see this for a while. See this for a while. So because of arrangement of actin and myosin, because of a proper arrangement of actin and myosin, because of proper arrangement of thin and thick filaments, you were able to see striations. Same type of arrangement was also found in cardiac muscle. Therefore, cardiac muscle also is exhibiting striations. But arrangement of thin and thick filaments in smooth muscle is random. You do not see this pattern wise arrangement in case of smooth muscle. Therefore, there you see zigzag lines and no proper striations. That's why it looks smooth or without any striations. Done. Now, again, coming to in-depth. Guys, focus here. This part of muscle cell, say this here. Okay. This part of muscle cell, and this here. That was the part where you see Z line attached to thin, and thin filament was not overlapped by thick filament, isn't it? There you see only thin filaments, right? There was only thin filament visible there, right? Visible. Guys, near Z lines, what you see was only thin filament. Okay, understood? So as all filaments in this point were exactly the same, we refer this structure as isotropic. Simply I band. I stands for isotropic. Iso means same. This is isotropic band. So let us color it. We can color it, no issues. Just color it with yellow. That will do. This is isotropic band. You can remove color at any moment, don't worry. Here also isotropic. Done. Whereas at this point you can see presence of both thin and thick filaments, right? So white are thin filaments, red were thick filaments, isn't it? Here also. See this carefully. Done. So as we can see, both thin and thick, and both are not exactly same, we can say this structure or band as anisotropic A band. A stands for anisotropic. Done. Therefore, you can see I band, A band, I band, A band, I band, A band, again I band. As you saw, alternate arrangement of ZM lies. Now we can see an alternate arrangement of I band, A band, I band, A band, I band, A band. Correct. Why it is called A band? Aniso, and absence, iso, same. Everything is not same, that they are different things. Therefore, aniso. Done. At the middle of aniso, at the middle of anisotropic band, guys, you can see there was a region where you see pure myosin attached to M line only, right? No overlappings, just myosin things, isn't it? This center part of A band, where myosin was not overlapped, but there is only myosin, this is called as H zone. H stands for Hansen's zone. H zone. Okay. So guys, I'm telling you again, A band has got both actin, myosin, and some part of myosin was in overlap. Some part of myosin was not in overlap. The part where there was no overlap with thin filaments is called as H zone. And which line was at the center of H zone? EM line, obviously. I'm telling you, once you understand structural details, it will be easy for you to go for physiological details. Okay. Okay. Now I band, A band. So let me color A band also. Let us color A band again with greenish. Green. So for you, I band is yellow, A band was green, right? Visible? Guys, I'm telling you basic fundamental aspects only, not going into depths. Because this was not the time. You need to understand what we're going to learn in 11th and 12th standards. You're here to learn basic things, not advanced concepts. Don't jump into advanced concepts without any basic knowledge. I'm here to give you that basic knowledge of things, how they work. It's so I band, A band, I band, A band, I band, A band, I band. Okay? Yes. Yes, Lakshmi. I, A, I, A, I, A, I. Correct. Alternate I bands and A bands. If we now zoom in, again you can see striations, isn't it? Striations of I bands between A bands, right? See, those yellow things were lines, what you are experiencing. So first Z line is attached to protein, to membrane, plasma membrane here. If you zoom out, now you can see bands very clearly. I bands are the lines what you see in a muscle cell actually, and I band is, what was the center of I band? Z lines. Therefore, arrangement of Z line and M line gave you an insight to see I bands and A bands. I bands have Z lines, A bands got M lines. Because of their arrangement, we can see striations here. That's why this muscle cell was referred as striated muscle. Understood? Keep it simple. Let us not get deeply into details. Just keep it simple. First learn bands. Then what happens during contraction? Guys, very simple. Actin can actually bind to myosin. Same time, myosin can also bind to actin. Actin has got myosin binding site, whereas myosin has got actin binding site. Actin has myosin binding site, myosin has got actin binding site. During muscle contraction, thin and thick filaments will touch and pull each other. I will tell you again. So is it clear till this point? We'll discuss it, no issues. Okay, we'll continue. It will be easy once you understand the concept of the structure first. Okay, H zone means, yeah Jayashri, H zone was at the center of A band. I did not show you that in picture, right? I'm showing you whole IA bands. Okay, done. So having you know this, so after letting you know these aspects, we can continue tomorrow with the concept of muscle contraction in basic concept, and also we'll count bones of your body tomorrow. Accepted? So all of us know that we do have 206 bones in your body, right? We'll count every bone in your body tomorrow. Accepted? We'll count. Okay guys, okay, thank you, signing off. Take care, stay indoor, stay hydrated.